Welcome to Systemic Stack. My name is Kabir Anand. This is episode 12 of the System Engineering series, and today we will explore Idempotency Basics in a way that helps you prepare for system engineering interviews on this topic. Now, being able to explain how to prevent duplicate side effects like double charging a user during a network retry is a huge signal to an interviewer that you understand distributed reliability. We'll dive into how to implement these safeguards so you can speak confidently about data integrity and API safety. This lesson starts by breaking down the core concept of safe repeated operations, defining exactly how idempotency keeps distributed systems predictable. We look at the vital role this plays in preventing duplicate effects, like making sure a user isn't double charged just because they hit submit twice. From there, we move into the actual implementation, where you will learn how to use idempotency keys and choose between different generation strategies. It's important to understand the backend flow here, specifically how we store keys and cache results to keep things fast and consistent. We'll then apply these ideas to high-stakes scenarios like payment processing and handling network retries, which is a favorite topic in system design interviews. To ground everything in reality, we'll analyze how industry giants like Stripe and PayPal structure their API headers to manage billions in transactions safely. By the end, you'll have a clear framework for building robust, failure-tolerant APIs that never compromise on data integrity. When we talk about building reliable distributed systems, we're really talking about how we handle uncertainty. Think about it. Every time a client sends a request over the network, there are three possible outcomes. The request could fail to reach the server could crash while processing it, or the response could get lost on the way back. Without idempotency, a client wouldn't know if it's safe to retry that request. This is why mastering this pattern is such a massive deal in modern API design. In an interview, if you're asked how to make a system fault tolerant, this should be one of the first things you mention. It allows the system to reach a consistent state even when the communication layer is unreliable. It is not only about handling errors, it's about designing your operations so that failure doesn't lead to corruption. We are basically building a safety net into the logic itself, ensuring that retrying a request doesn't lead to unintended side effects. Let's look at what we mean by safe repeated operations. The core idea here is that performing an action multiple times should produce the same final outcome as doing it just once. Imagine you're at an elevator and you press the call button 5 times. You don't get 5 elevators. The system just knows you want to go up. That's idempotency in action. In software, this is crucial because it eliminates the fear of duplicate work. If a process hangs and we aren't sure if it finished, we can just run it again. If we don't have this safety, we're constantly stuck in a limbo that usually leads to manual cleanups or inconsistent databases. Failure to implement this correctly often results in zombie resources or double billing, which are absolute nightmares to debug. When you're explaining this to an interviewer, emphasize that idempotency is what lets us build self-healing systems that can automatically retry without needing a person to step in. To get technical for a second, an operation is considered idempotent if it can be applied multiple times without changing the result beyond the initial application. Now, don't confuse this with nothing happening on the second call. Something does happen. The server recognizes the repeat and usually returns the same success response it gave the first time, but it doesn't actually perform the underlying state change again. It's like a math function where f of x equals f of x. If you set a value to 5, setting it to 5 again doesn't change anything. However, creating a new record usually isn't idempotent by default unless you specifically design it to be. In a system design interview, you'll want to distinguish between operations that are naturally idempotent, like a get or a put, and those that require extra work, like a post. Understanding this distinction is the difference between a junior developer who just retries everything and a senior engineer who builds systems that handle those retries safely. One of the most common reasons we use idempotency is to prevent duplicate effects. You've probably seen those warnings on checkout pages that say, "Do not refresh this page or click back." That's basically the developer admitting their system isn't idempotent. If a user clicks submit and the network times out, their browser might try to send that payment request again. If your backend isn't prepared for that, you might end up double charging the customer's credit card. That's a huge failure mode that leads to massive customer dissatisfaction and expensive support tickets. It is not only about payments though. Think about creating a new user account or an order. If the request is resent because of a jittery connection, you don't want two identical orders in your database. By making the operation idempotent, the server can see that it has handled this specific request before and simply refuse to execute the logic a second time. It keeps the system clean and predictable. From a systemic perspective, idempotency acts as a critical safeguard for data integrity. In a distributed environment, you have multiple services talking to each other, and they often use message queues. These systems usually guarantee at least once delivery, which means a message might show up at your doorstep more than once. If your database logic isn't idempotent, those duplicate messages will slowly poison your data consistency over time. You'll find balances that don't add up or inventory counts that are completely off. This is why financial systems are so obsessed with this pattern. It ensures that even if a message is replayed 10 times during a recovery process, the final state of the database remains perfectly accurate. When you're in an interview, you can frame idempotency as the bridge between at least one's delivery and exactly one semantics. It's the mechanism that turns a messy, repetitive stream of events into a clean, reliable record of truth for the entire business, which is a major signal of seniority. So, how do we actually build this? The most common way is through the use of idempotency keys. The client generates a unique string, usually a UUID, and attaches it to the request. When the server receives it, it checks its idempotency store to see if it's seen that key before. If it has, it just skips the actual processing and returns the cached result from the first time. This is a brilliant architectural pattern because it puts the responsibility of identifying the intent on the client. It solves the lost response problem perfectly. If the client doesn't get a response, it just tries again with the exact same key. The server sees the key, realizes it's already done the work, and just hands back the original success message. One thing to watch out for in an interview is the storage of these keys. They need to be stored in a fast, reliable place like Redis, and they must persist long enough to cover any reasonable retry window. There's a bit of a trade-off when it comes to how you generate these keys. On one hand, you have client-side generation using something like a UUID. This is great for binding a specific request to an intent, but you have to trust the client to generate it correctly. If the client accidentally uses the same key for two different orders, you've got a major problem. On the other hand, you can use natural keys from the business domain, like a combination of a user ID and an order ID. This can be more robust because it's tied to the actual data, but it might not be flexible enough if a user needs to genuinely repeat an action. Most high-scale APIs, like Stripes, lean toward the client-generated header approach because it's flexible and decoupled from the internal data structure. When you're discussing this, mention that the choice depends on your trust level with the client and the specific requirements for how long a duplicate should be blocked. Let's walk through what's actually happening on the back end. When a request hits the server, the very first thing it does is look for that idempotency key. It checks a fast access store to see if that key is currently in flight or already completed. If it's already completed, the server retrieves the previous response and sends it back immediately. No database writes, no external API calls, nothing. If it's a brand new key, the server marks it as processing and goes ahead with the logic. Once it's done, it saves the result and marks it as succeeded. This check then act flow is a classic pattern, but you have to be careful about race conditions. If two identical requests hit two different server instances at the exact same millisecond, they both might think they are the first one. That's a huge failure mode. To solve this, you need atomic operations or distributed locks in your key store to make sure only one process can claim that specific key at a time. Payments are the classic use case for a reason. Imagine a user is on a slow mobile connection and they hit Pay Now. The request goes out, the bank processes the charge, but the success message never makes it back to the phone because the signal dropped. The app sees a timeout and naturally tries again. If you don't have idempotency, the bank sees a second request and charges the user a second time. Now you've got a furious customer and a messy refund process to deal with. By using an idempotency key, the payment gateway recognizes the second attempt as a retry of the first. It sees that the charge was already successful and just says we're all good, without touching the user's balance again. This is why you'll see an idempotency header in almost every professional financial API. It's the primary defense against the chaos of unreliable networks and impatient users who just love to double-click when things seem slow. Beyond just user actions, idempotency is a lifesaver for background jobs and automation. Let's say you have a worker process that's responsible for syncing data between two systems. If the worker crashes halfway through, you want to be able to just restart it and have it pick up where it left off. Without idempotency, that's incredibly hard because the worker doesn't know which records it already processed. You might end up with partial updates or duplicate entries. With idempotent operations, the worker can just blindly retry everything. It sends the same data again, and the receiving system just ignores anything it's already handled. This makes your automation much simpler and more robust because you don't have to write complex state tracking logic for every single failure scenario. You just embrace the retry. In an interview, highlight that this simplifies the error recovery logic significantly, allowing developers to focus on the happy part, while the idempotency layer handles the messy what-ifs. One of the trickiest things to handle is when a response is lost in flight. The server did the work, the database is updated, but the client is sitting there wondering what happened. When the client retries with the same key, the server must be smart enough to ignore the request, and more specifically, to actually return the original result. If the server just returned a generic already processed error, the client might not know if the previous attempt actually succeeded or if it failed for some other reason. This is why caching the full response, including the status code and the body, is so important. It ensures the client gets the exact information it would have received the first time. A common mistake here is not having an expiration policy for these keys. You can't store every key forever, or your database will eventually explode. You have to decide on a validity window, say 24 hours, after which the key is cleared and the request is treated as brand new. If you look at the industry leaders like Stripe, PayPal, or Adyen, you'll see they all follow this pattern almost exactly. They've standardized the use of an idempotency header. These companies process billions of dollars, and this simply couldn't function without this safeguard. It's become such a standard that if you're building a public-facing API today and you don't include some form of idempotency for state-changing operations, it's considered a major architectural red flag. When you're in an interview, referencing these real-world examples shows that you're not just talking about theory. You understand the practical standards that the industry relies on. It also shows you understand that consistency and reliability are part of the product's value proposition, not just technical details. These companies have effectively offloaded the complexity of handling network failures onto a well-defined, header-based contract that both the client and the server understand perfectly, which makes their platforms much more developer-friendly. Let's look at the actual implementation in a request. Most of the time, this is handled through a custom HTTP header. You'll see things like idempotency key, followed by a unique value in the request metadata. The beauty of using a header is that it keeps your actual request body clean and focused on the business data. It separates the intent to do something from the metadata about the request itself. This makes it much easier to implement across different endpoints without having to change your data schemas. Some systems also use a request ID header for similar purposes, but usually an idempotency key is specifically reserved for ensuring that the side effects of a post or patch request only happen once. When you're designing your own APIs, think about where this logic lives. Does it live in your application code, or can it be handled by a middleware or a gateway? Ideally, it's a reusable component that your developers can just plug in. So we've walked through why idempotency is actually the backbone of reliability in distributed systems. It's the guarantee that repeating an action won't cause unintended side effects, which is absolutely vital when network failures are inevitable. In a system design interview, you've got to be ready to explain how idempotency keys serve as that unique fingerprint for each request. Whether you're using client-side UUIDs or natural business keys, the logic remains the same. Recognize the duplicate, skip the heavy lifting, and return the cached result. We also touched on the trade-offs, right? Adding this layer introduces some storage overhead and architectural complexity, but it's the price we pay to prevent critical failures like double charging a customer. Ultimately, mastering this pattern is about protecting data integrity when things get messy over the wire. You're now equipped to justify this choice whenever consistency is on the line. So that brings us to the end of our look at idempotency. Now, if you're heading into a system design interview, remember that just mentioning a key isn't enough. You need to talk through the storage trade-offs and how you'd handle race conditions when two identical requests hit at once. Well, showing that you can navigate those failure modes proves you're thinking about real-world consistency, not just happy path code. I hope this gives you a solid edge in your prep. For more topics like this, definitely subscribe to the channel and check the description for all the course details. Good luck with your studies, and I'll see you in the next one.